well. What we've shown is that the untrusted code can't access global variables in the hosting page. But we didn't really prove anything about how one piece of untrusted code could influence the execution of another piece of untrusted code. So there's nothing so far to prevent me from writing a malicious Facebook application that doesn't attack Facebook. They're protected, but attacks somebody else's application. So I might be competing with somebody else for the success of my Facebook application. I could download their code, reverse engineer it, figure out a way to kind of interfere with it, put my interfering code back up on Facebook, and carry out some things that I really shouldn't be able to do. So how do we solve that problem? So there are basic problems so I shouldn't really point to Facebook as a company as being at fault. These are sort of fundamental limitations with the methods that I've talked about so far. And here, I guess the basic communication channel, to sort of cut to the main idea, is that there are these native built-in objects that every application has access to. And the dynamic nature of JavaScript lets you add kind of properties or additional data tagged on to those native built-in things. And so that provides, first of all, a communication channel between different applications that want to communicate, and a communication channel if I know what some other application is doing that lets me manipulate its data if it stores it on a global object. And now I don't know about the videotaping business. So this, I think, may or may not have been fixed. So we'll just do this quickly. So here's a method that redefines the way functions work in JavaScript that can be used to kind of break other applications. Maybe I'll leave it at that. Where's the videotape going? Yeah, okay, maybe we'll just not show this on YouTube right now. Is that okay? Because just this piece of it, okay? Current functions are multi-argument functions that take their arguments one at a time. There's this bind.apply idiom for taking a function of multiple arguments and applying it to its first argument and then producing as a result a function that takes the rest of the arguments later. And this, for various reasons that are detailed but I'm not explaining, having to do with this mechanism, let's call it, lets us redefine this function. And then other application that's using curried function application kind of gets turned into, gets subverted and can be reconstructed to behave differently by this attacking application. So this is to show you that we didn't overlook a trivial problem. We didn't solve another important problem. And so for this, it seems like our mechanisms of code filtering, code rewriting, and wrapping native applications, our analytical framework and our understanding of defense mechanisms just doesn't seem to be up to the problem. But we've talked with the Google Kaha group, and they're interested in this capability model. And so our current work is to try to figure out how to kind of follow the same process, take their kind of informal ideas, things they believe should work, and study this scientifically, see if we can either prove it correct or most likely in the process of proving that some of their ideas work, kind of weed out the ones that need a little bit of improvement. Haven't done that yet, so could be everything they did is right, but past experiences suggest we'll probably find something here. So capability-based protection is a traditional thing in operating systems. There's some effort to adapt this to programming language contexts. And there's a bunch of work on what's called the object capability model. It's fun to read. They have some really good ideas. There are a bunch of language examples. So in each case, E is a subset of Java that's meant to be capability safe. Joe E is another subset of Java that's meant to be capability safe. Emily is a subset of OCaml that's meant to be capability safe, and W7 is a scheme-based capability safe language. The idea of capability safety is code can do only can do things through explicit references that are granted to that code. There's no kind of way to access data that you're not explicitly passed at the beginning of execution. So in trying to work through the object capability literature and formalize things and prove stuff, we kind of came along across a slightly more general concept that we call authority safety, which are some safety conditions sufficient to prove isolation properties. And then we look at the capability model as a way of achieving authority safety in different programming language contexts. And the main idea here, just to point to one thing, is that our notion of authority safety is a semantic notion, a notion that's preserved by program execution. And that's what makes this concept useful. And another piece of evidence that it's a useful concept is that almost all of our attacks against Facebook and AdSafe and other things have to do with someone thinking they got the solution right, but not realizing that the property they set up at the beginning kind of dissipates as the program executes. So this safety property preserved by execution seemed to be a useful concept. And then we have some work on this that's recent, where we show that capability safety implies authority safety implies isolation, and languages like these satisfy our conditions. So it seems to be a theoretical framework we're developing that's adequate to talk about this isolation of mutually untrusting applications. And the next phase of this work will be to actually look at more of the details of this Google Caja system, which is relatively complex, and see if we can carry out our analytical process there. So I'll wrap up. I think to kind of just step back a minute, the three main points are, one, I think the web is really a great artifact to study with computer science research. I think there was been a phase where people looked at the web graph and graph theory on the web, and there are lots of nice results in that area. Somewhat less work, I think, given the prominence of the web. I don't think this thing is going away, right? I don't imagine we're going to have no web in 5 years or 10 years. So this is kind of our biggest, most interesting distributed system. So shouldn't there be, instead of a compiler course, a web course? Or in addition, or in parallel? It seems like this is important in core computer science. There's a lot of great challenges here. It's fun to do research on this because people know about it. And as I said, many things are open. So advertising web research, and in particular web security, has been fun for us. And I think there's room for many more. In this particular sandboxing of untrusted JavaScript, I think we've made some reasonable progress. There's still some remaining problems. And there are many more kind of scientific problems about the web as an application execution environment. What works about it, what doesn't, how to get nice models for developing web applications, how to provide security mechanisms, and so on. So many, many questions. I think you could make a career or start your career by reading the last 3 years of, let's say, dub conference papers, none of which have any analysis whatsoever, for the most part, maybe 1 or 2%, and saying, is this really true? On what basis are they claiming this mechanism works? Could I prove that? That, I think, would be a perfectly reasonable paradigm to get started in this area if you're interested. So there is some related work along the lines we've talked about. This is a few of the things. Most of the work has been on kind of smaller subsets of JavaScript and so on, but I'll leave that some pointers to related work just so I don't overlook the fact that we're not the only people who've ever looked at JavaScript. But I think I'll end with this concluding slide and wrap up here. So thank you.